This is lecture 2 on the topic of wave mechanics, part 1, because the second part will follow a couple of lectures later. It's a mathematical or theoretical physics course called quantum mechanics at senior level, and the first author of the text I'm using is Davies. Here's the text called Quantum Mechanics, the second edition, by two authors, Paul Davies and David Betts. You can get this book for free on emule, that's emule.com, or if you prefer in paper form, hard copy, then you can pay for it. You can go to Amazon.com and probably get it secondhand. And the prices and all those kinds of details about both the course, the text, you can find on my website, which is here. So Prof. Hugo deGaris, Prof. short for Professor, Hugo deGaris is my name, .wordpress.com. And then click on the tab, deGarisMPC. So M for pure mathematics, P for math physics, and C for computer theory. Because I give lectures on all three, but mostly pure mathematics and mathematical physics. This is this course here is the second one that I've been recorded. The third one will be on computer theory, theory of computation. So that'll be the C. So I've already given a math course that was on finite group theory at junior and senior level. Currently giving now a physics course, the P, and the third one will be computer theory. That'll be the C on theory of computation. And the fourth one, recently decided, will be on special relativity. So another physics course. Right. So before I get into the nitty-gritty, I'd like to say it's quite possible, if things continue the way they're going, that this may be I really hope, the last lecture that I will record in standard resolution, STD, standard. When I originally bought the camcorder, the Sony Handycam, my intention was to film in high definition because of its wonderful clarity. The problem was that to film in high D takes a lot of gigabytes, and to upload even just say 10 minutes of high definition film video to YouTube costs me half a day, literally. So that was just totally impractical. So I went back to standard STD, standard resolution, which is fuzzier. So the writing on the board was not clear. That was my biggest problem. Now I've adapted somewhat. For example, I've learned to give these recordings during the daytime, because the daylight seems to make the readability of the writing on the board easier than with night light. I got a bigger board. I write bigger. So I've been adapting. But these are all just stopgap measures. What I'd really like to do is to just film in high definition. So the next step will be to do that, and then to what's the word? When you shrink the size of a file, to compact it, condense it. And there's a technical word, compress. Yeah, compression. So now I have a friend who's helping me with experiments on compression, to take a high definition file and compress it down to something that's of more or less the same order of size as the standard resolution files that I'm recording right this minute. Okay, and then upload them to YouTube, which takes about 4 hours per 12 minutes or so. That's what I've been getting lately. So that rate's okay, because if you think about it, 12 minutes or so per 4 hours. It's relentless. The upload to YouTube is relentless. It just keeps going. So that's 5 or 6 video clips per day, and that means you have to lecture per day. So it keeps you busy. So that rate is okay. So hopefully soon, maybe unless there's a new problem, the whiteboard you'll be seeing and me in high definition, which would be very nice. Okay, that being said, let's start. Now, let me say a little bit about this term wave mechanics. What is that? Well, in practice, it's just solving Schrodinger's equation. That's really all it is. It's what it boils down to. Okay, and so it's sort of analogous to quantum mechanics, but with the emphasis on the word wave, because we're talking about Schrodinger's wave function. This psi here, Schrodinger's wave function, like his Schrodinger's equation. Now we've already done this 2 sessions back, I think. Now, so what I'm going to do now is I need to adapt the Schrodinger equation somewhat so that it's possible to put in a potential energy term, a V. This is the potential energy. A bit of quick revision on what is potential energy. You go back to fresher level, even high school level physics. If I lift something up, I'm giving that object, especially in a gravitational field like the Earth's, I'm giving that object the potential to have kinetic energy, the energy of motion, because when I let it drop, it will gain kinetic energy as it accelerates. And so when it's at this level where it started with, I can do it again. So raising it by this much in a gravitational field gives it potential energy to allow it to have kinetic energy when I let it fall. So that potential energy, you just call it V. Now that's for gravity, but I could take, for example, a spring like this, and I stretch it. That's giving the spring potential energy, right? Because when I let the spring go, let's say there's a weight, a mass on the end of the spring. So here it is, and I just pull the spring out, and then I give that spring potential energy, because when I release the mass, it'll go, it'll have kinetic energy, right? So I now need some potential energy term, V, in the Schrodinger equation, because the next 4 chapters, this is the first of 4, will involve different situations that the Schrodinger equation is solved in, right? So in practice, I will be using different values for this potential energy V in different situations. So I need to bring this potential energy V into the equation. So so the main idea, now we've done this sort of thing before, so I'll go through it fairly quickly. But I need this version of the Schrodinger equation with this V psi term in it. Now before we didn't have this. This was not there. We just simply had this second differential, and this with respect to x, and this first differential with respect to t. That's all we had. This middle term here just wasn't there. But we need it because, well, having it, we can now solve Schrodinger's equation in different environments, different conditions, where the V changes, different setup. Okay, so before we just had this, like the energy was just the the kinetic energy, the momentum squared divided by 2m. That's from classical mechanics. Okay, you've probably done that in high school, or fresher level physics if you've done it. Okay, well now we're going to add another energy term. So E now is not just kinetic energy; it's the total energy. Right? It's the kinetic energy plus potential energy. So P squared over 2m plus V. Right? So that's our motivating, well, that's what we sort of start with. Now for, let's see. Most of this then is just the same as we've done already. So I'll go through it fairly fast because it's just revision. Okay. Now what's this? This, momentum is h bar k. K by definition is just, it's called the wave number. So it's defined as just 2 pi divided by the wavelength. The wavelength of what? Of de Broglie, the French guy. De Broglie wavelength of a particle. It's the particle's wavelength. God, that sounds strange. That's quantum mechanics, right? A particle is associated, whatever that means, with a wave, okay? And the wavelength of that particle's wave is inversely proportional to its momentum, right? So this is the de Broglie relation, okay? Well, here it is here. The wavelength is Planck's constant divided by the momentum of the particle. Now, you've also got E is equal to h bar omega. Now, what's that? That's the energy of a photon. Okay, so omega by definition is just 2 pi times the frequency. We don't want to be writing down 2 pi's all the time. It's sort of inconvenient. So the math physicists have invented these terms like K and omega. So omega, three bars here, meaning by definition. So omega is just 2 pi f. All right. Now you've seen this before. This is sort of a general form of a wave, an oscillating. So it's in the exponential form instead of. This is a shorter way of writing, like cosine. That's a waveform, or sine waveform. You just write it for mathematical convenience in this complex number notation, exponential to a power. Now, we've done this before, but say you start at x is 0 along the x-axis. So imagine here x is 0, and then you move along the axis a full wavelength, a lambda. So your x now will be lambda. So you've got lambda over lambda. So that's just 1